Hello. This lesson today is going to focus on Lechatellier's principle and mainly on predicting effects on equilibrium from changes in concentration, temperature, and the presence of a catalyst. First, we will look at the effects on equilibrium from changes in concentration. So take the hypothetical equation. A plus B yields C and D. In this case, A and B are the reactants and C and D are the products. When the reactant's concentration increases, the reaction shifts towards the products. So for this hypothetical, if the concentration of A increases, it will shift towards C and D. On the other hand, when the product's concentration increases, the reaction shifts towards the reactants. So now let's look back at the hypothetical equation, and if the concentration of C increases, the reaction will shift towards A and B. A quick way to remember these first two rules is to associate adding components of the reaction with shifting away or in the direction opposite of where it was added to. Simply, I tend to think of it as add away. Contrary to increasing concentration, when the concentration of a component decreases, the reaction shifts back towards where it decreased. If the concentration of a reactant decreases, so in this hypothetical, let's use A, the reaction will shift back towards the reactants, so in this case, it will shift towards A and B. Similarly, if the concentration of a product decreases, the reaction will shift back towards the products. So in this hypothetical, let's say the concentration of C decreases, then the reaction will shift back towards C and D. Now let's look at the effects of changing temperature and equilibrium. When temperature increases, the reaction shifts away from the heater energy. This favors endothermic reactions because the added heater energy is on the reactant side, meaning it will shift towards the products when the temperature increases. When the temperature decreases, the reaction shifts towards the heater energy. This favors exothermic reactions because the heater energy is on the product side, meaning it will shift back towards the products when the temperature decreases. Now let's look at some examples. Let's take the equation N2O4 yields 2NO2, and in this case, the delta H of the reaction is positive 57 kilojoules per mole. Because the delta H is positive, making it endothermic, you rewrite the equation with heat added on the reactant side. So now if you increase the temperature, it will shift towards the products, and if you decrease the temperature, it will shift towards the reactants. Now let's use the same equation, but let's change the delta H of the reaction to negative 57 kilojoules per mole, making the reaction exothermic. This means that the equation can be rewritten with heat added to the product side. In circumstances like this, when the temperature increases, it shifts towards the reactants, and when the temperature decreases, it shifts towards the products. Lastly, let's look at changes in equilibrium in the presence of a catalyst. Well, spoiler alert, when a catalyst is added, there is no change in the equilibrium. This is because a catalyst affects the rate of the forward and reverse reactions equally, therefore counteracting any changes in equilibrium.